Hey there.
Hello.
Hi. All right. So we left off. We were talking about motion. And we were talking about forces,
Yes.
actually. That's right. So, yeah. What do you want to do? This is the last hour, I guess, for your test. So, what do you want to work on?
Let me get this in front of me. Okay. If we could work on
What do you think?
if we could go to the section that says like projectiles.
Okay, so that was a couple weeks ago or something.
Yeah, that's like some of the most recent stuff.
Oh, okay. Let me go to the email. Find it. Yeah, I don't think we actually covered these questions yet because there was a test coming up. Is that what we did? It's the same as the monkey, the free fall and the monkey and all that stuff. And the projectile motion was in that same batch of notes, right?
Yeah.
It should be not here on the 5th, I guess. Maybe on the 10th. Where are they? That's my notes. All right, we got something from the 7th. Let's see, maybe this is it. Yeah, here we go. All righty. You want to start at the first one? Have you worked these out yet?
Wait, which paper is it?
Projectile motion. Number 1 is a person driving on a horizontal roadway loses control of their vehicle. Is that what you were talking about? Or something else?
Oh, I don't know. I think I sent it to you. It's in the
Oh,
same packet as the other stuff, and it says projectiles in two-dimensional motion.
gotcha. And this was what you said yesterday, right? The most recent one. Okay.
Yeah.
Yeah. Sorry if you said that I was not paying attention. Great. So here we are in directions, projectiles, and two-dimensional things. Okay, great. All right. So before we get into it, free fall. You got to understand free fall because that's 1/2 of projectile motion. So if you understand projectile motion, then you understand free fall. Okay. So skydiver jumps out of an airplane, flying out of an altitude of 12,275. So as always, okay, hooray for us. We know what to do with this. Any numbers, we know it's a distance. Why? Because it's in feet. They're jumping out of an airplane, flying at altitude, and his parachute fails to open. Okay, that's it. You might think, oh, garbage information, but parachute fails to open means ignore air resistance. We kind of had a conversation about this, right? And don't ever take into account air resistance when you're doing those qualitative problems about where will the box, this is a plane, and a box falls, right? Well, parabola always. If you include air resistance, as you saw before, it would go like that because the air won't really act like that, but no air resistance, okay? So anyways, I've said my piece about that. How long does the skydiver have to live? Poor guy. Okay, so this is free fall, which is part of projectile motion. How do I know that? Because it's one dimension. And we know that because we're going to draw a picture.
Okay.
Picture is the second step. Extract as always. We know that we're on Earth. It doesn't say that, but it's on Earth. And so another piece that we know, what's the value of little g?
Oh, is it negative or just regular 9.8?
It's good practice to use negative. Yeah. So
Okay.
it'll help you. And the units, it's acceleration, right? So, and only on Earth. So now draw a picture. What's happening? He jumps out of the plane. I don't care. That's my guy. Remember, we treat him all as point particles and it's at a height. That's when he initially falls. And so this is how you would do it. And you say height, if that's the variable you're using. Hopefully you're familiar with me using different variables. It could be D, That might be actually what you normally use, but again, it doesn't matter, right?
Mhm.
So height, great. And we have G, and they say how long? How long does this guy ever have to live? And so you look at this and you say, what equation, right? This is I've set it up now, and now identify the equation that you need. What do you think the equation is?
So we're trying to find the
Sorry, time.
so we're trying to find the time.
Mhm.
So it would be t equals the square root of, is that right? No.
That is the equation. It's just you've solved for the, oh no, we're solving for t, so that should be good. Square root of what?
Oh wait, is it?
I believe this is the normal equation. And then when you solve for t, if this is what you're going to say, hopefully.
Mhm.
Now, so, okay, I want to make sure now I know, because you use d, right? I don't want to confuse you any more than is necessary. So d is the distance, our height, great. But g is the acceleration. And our key here is that that's acceleration, always units for acceleration. So we can erase that and call it a, because it's
Okay.
the only thing that works, right?
Mhm.
So hopefully now you can see I got to plug this baby in, and it's easy. And you say, okay, 12,275 divided by negative 9.8. Well, you get an error in your calculator, right?
Mhm.
And so how do we deal with that? Well, we say absolute value. Let me make it
Yeah.
exactly. So d divided by the absolute value. So now you might be asking yourself, well, why did I say you should use the minus sign? Because that's what you normally do, and that's how you should think about it. But you got to be careful when you're dealing with this is called the domain, right? This is undefined for negative numbers, so it doesn't work for calculators, even though we know what's going on, right?
Mhm.
So what'd you get for t? Oh, actually, I'm missing a part. Do you know what it is?
Is it the square?
The hint here, I'll give you a hint. It's the units. What I have to do.
Oh, you have to convert them so it's the same.
Exactly. So how do we do that? There's two ways to do it, right? You could turn this into meters, but the way that I saw in your notes is that you're converting this to whatever feet per second squared, I guess. So you're converting meters to feet.
Okay.
So I think we know that, right? It's 3.28. Let's write it down. 3.28 feet equals 1 meter. Yeah. So if I believe this is what you did before. You said, okay, A is equal to 9.8 meters per second squared. And then how do I get it to feet? Well, I have to do our normal thing, right? So 3.28 feet per 1 meter. I don't think this is exactly how you did it, but hopefully it's clear. I think you did it all in one go. Where what I mean by that is you said t is equal to the square root of 12,275, and then you did it in the equation.
Mhm.
And so it doesn't matter, of course, but I just want to make sure you understand what's happening and why. That's really the most important thing. So I'm punching in the numbers here. It's 32. I think we talked about before. If you don't remember, if you, I don't know if what he wants you to do, but it's 32.1. So in case, I know it's an extra thing to memorize, but if you need to go to feet, it's just 32.1 or 32 should be okay. I know I for sure wouldn't be taking many points off for that if I was the instructor. And I got 19.5 seconds.
Okay. Let's see. Yes, that's what I got too.
Seconds, and it's got to be in seconds, right? Because of this unit here. Okay, but that's an aside. It looks complicated, and it's hopefully it's not, because it's actually not, but it doesn't mean it's not complicated for you, right? I hope that it was clear enough. It's really this thing that might trip you up, right? But we're just converting. So any questions on that one? We can definitely do another one. But part two here, number two is actually part two of this whole problem. So I wanted to do that, and then we could do another one if you want. But do you want me to talk about anything here? Go over anything on this particular one?
I don't think so.
Okay, good. Okay, so now look at number two. I'm going to ask you, why don't you walk me through it and see if you can do this one.
Okay, so how fast will we do? Okay. So is it the same equation?
So what do we need? That's what I'll answer your question with a question. What are we trying to find? What do they want from us?
Oh, they're trying to find the speed.
Speed, which is, what's the variable for speed?
S?
I just realized it. I would use V for velocity, because you're 100% right, but they're talking about velocity. And when you're dealing with acceleration, you always use velocity. So now that you asked me, is it the same equation? I think you can answer that now, right? Does V show up?
Oh, yeah.
Right. So, but you're getting ahead, right? Because epic means extract what you have, draw a picture, and then identify the equation. Now it's okay, usually stepping forward, but if you're having trouble, start with extract. And what does extract mean? What's all the given information? Now, so far, we don't have anything. We have that. We need some values. So where are we going to get them?
The problem above.
You got it. What do we write down?
Okay, so I think the equation is A equals VF minus VI over T.
Yes, you can use that one. So we never, yeah. Another one would be, or sorry, that is the equation, right? And then, so how do you solve for VF? That's what yes. So yes, 100%.
Okay.
And so what do we need if we're solving for that?
Okay, so if we're trying to find VF, then we need, okay, so the time is 19.54 seconds.
You got it. What else?
And then VI and A. So is the initial velocity 0?
Yes, it's important to know why. So you don't have to say it out loud if you want, but hopefully you know. And
then the acceleration is negative 9.8.
always and forever in projectile motion, in free fall. But yeah. So now, yeah, that looks like everything. So what's the next step?
Okay, and so then you have to isolate VF.
Yep. So how do we do that?
So first you multiply by t, and then you get t times a equals vf minus vi,
Good.
and then you just add vi.
You got it. We always, if we're subtracting, we got to add to cancel. So we would, if we did a straight line thing, plus 0, right? So then we get VF by itself. Exactly right. So I'll plug it in, and you should do that too. Let me know when you got it.
Okay, I got 191.492.
Yeah, that's what I got as well. And that's good. That's the correct answer. Why? And we have a minus sign here, right? But they're not asking us for velocity, really, right? So I don't know if you meant that, but how fast just means speed, which is a scalar, right? No direction. And so magnitudes are always positive. So yes, if they were asking for velocity, you would say minus, because the minus indicates, oh, straight down. That makes sense. The velocity is pointing in the direction of motion, right? Which is straight to the ground. So little slide things that, from what you told me, it seems like he will, pay attention to that. And if you put minus 191, he'd probably give you a point off, I guess. So that was good. And you did that one. I didn't really help you with that one. So that's a good sign. That means you know it. It's good. A little help in the beginning, but you did fine on that. Okay, so the next one, find all the lines. So okay. So it's crossed out, number 3. That means no projectile motion, maybe. I know that's
Yeah, we haven't really gotten to that.
That's great, because it's usually difficult, and it can be, especially the first time you're learning it. And so that's good. You got a bonus there. Okay, so I know it says projectiles in 2-dimensional motion, but both of these were not 2-dimensional motion because it was just straight down, right? So that means just 1 dimension. So let's do another one. Let's say, okay, so no projectile motion. Okay. Okay, a ball is dropped. Ball is dropped from rest. All right. Same type of problem, but it's a little bit different because it feels like you got it, and obviously I'll walk you through it too. But yeah, you want to go through it?
Yes.
Okay.
Okay, so this is so we're finding the velocity. So that is the the A equals VF minus VI over T. Okay, and then okay, so okay, so we are trying to find how long it takes. So T is the unknown.
Yes. We got two things actually they're looking for, right? In the same question. Same as last time, it's just you'll see it in the same question sometimes.
Oh, okay. So
they want both of these
okay.
things, right?
Yes. So
And what do we know?
we know VI
Sure. What is it?
0.
Good. For
And
rest.
then the acceleration is 25 meters.
Doesn't have the right units, right?
Oh yeah. Okay.
What type of problem is it? You know what I mean? Like, is it Newton's laws? Is it projectile motion? Is it one dimension? Like on the ground? Is it free fall?
Well, the part where it says how long does it take, that makes me think it's free fall.
Yeah. I mean, dropping the ball from rest, you're right, it's free fall, but it's the ball dropping from rest from a building, right? Because once you release that thing, that's free fall. I mean, so that's why, but you're right. So what is A in free fall?
A in free fall is I'm not sure.
Little g?
Oh, okay.
Always and forever. What is that value?
A is negative 9.8 meters per second.
Squared. Yes.
Yes.
Good. Is there anything else? Got a number up here we haven't used yet.
25 meters. That is that's like the distance.
Yeah. So what do we use for that? The variable?
D.
Got it. Okay. So yeah, there's nothing else, but we have two things to solve for here, and they both show up in this equation. Do we have another equation for these guys, for all of them? All 5 of these, or just maybe 3 of them?
A equals 2 times T over T squared.
Yes. Perfect. I forgot that too, actually, when we did the other problem. So our numbers are wrong, but it's okay. We did the whole thing right, except at the very end. But yeah, there's that factor too. So now what do? Now we can solve for something, right?
Mm-hmm.
Okay. So what are we solving for if we have these two equations?
We could solve for okay, so the first one, in the first equation, you're solving for the wait, wouldn't it make more sense to do the second one?
Yes, definitely. You have to.
Okay.
Good. And the reason is we have, this is unknown and so is that, right? If we only have one equation, we can only solve for one thing. So that's good. So we're solving for t down here, right? Because we know A and D.
Mm-hmm.
Make sense?
Yes.
Okay, so we can do that there. And so A, okay, I wrote it, I did it completely wrong before. That should be what it is, right? Because I didn't start here and I just kind of,
Mm-hmm.
no. Okay. D squared both sides, right? And so I have to divide by A, so it is 2D over A, but then square root, which means a magnitude down here because we can't use the minus sign, right?
Mm-hmm.
So now we can figure that out. And just like we're doing exactly what we did before, just kind of in a different format. And I wanted to give this to you because a little bit tougher. And if you can do this, then you can do anything he throws at you on that test, okay?
Okay.
So we'll do it. I'll just write it down, make sure you get it, right? But before we do that, what do I do now? I just got this answer for time. That's how long it took. It takes 5.1 seconds to fall. Great. Am I done? Or is there another thing to do?
Oh wait, did I do something wrong? Because when I did everything, I got 2.258.
I might not have done my square root. Nope. Yes. Sorry, a little tired, but yes, you're 100% right. I forgot my square root. So 2.26, that's how long it takes.
Okay.
And then what do we have to do? Or are we done?
With
They still want this, right?
yeah.
Yes. And we have this equation here for it, so we can simply plug all that stuff in. So if I did that, I would get minus 9.8. We can use the minus sign now. VF, we don't know. That 2.26. Or you can solve for the first thing. Usually we do that. So it would be solving for VF. You would have this, right? AT plus VI, which minus 9.8 times 2.26 plus 0. But of course, that's the same thing over here. So 9.8 times 2.26 minus 9.8. And this is when you would want to use that minus sign because they're asking you, they ask, what is the final velocity? Now we have a minus sign because velocity is a vector and it points straight down. That's what the minus sign tells us. So, like I said, a little bit tougher on these ones, but it is the same sort of thing. And I think you did fine. And like I said, if you can do this one and understand it, then you can do anything from this section in free fall.
Okay.
So is there anything you want to go over for this one?
So for the second part of the question, when you start doing the VI minus or VF minus VI, and then you plug in everything, so it's like the 2.2 times the acceleration.
Yes.
Why do you not do the like absolute value for that part?
Because they were asking for final velocity, and velocity is a vector, which means it has to have a direction. Yeah. And velocity is always in the direction of motion. I drop something, well, its direction of motion is towards the ground, right?
Oh, okay.
And we usually say that up is positive. That's why we have a negative sign. That's why we have a negative sign here, because we're saying that up is positive. Make sense?
Yes.
Maybe I over answered, but it's because velocity is a vector, and all that stuff we talked about before, scalars and vectors. There'd probably be a couple qualitative questions on it. Is this thing a vector or is it a scalar?
Yeah.
Okay. Good. Promise.
Yes.
Okay, cool. We can do another free fall. I can go get a problem. I guess it'd be okay to make one, a simpler one if you want, on free fall, or we can move to another topic here. We still have a decent amount of time, but not not a lot. So you should, if you want to move to something else, you should pick something, one of your weaker, whatever you think is weaker, or if you want to go back to gravitation,
Can we go to, there's like an ellipse and it says like label the parts, and then above that it says calculate the eccentricity.
So you want to calculate the eccentricity? Okay. Are you good on the parts of the ellipse? It's kind of, you don't really need me for that. You can look at your diagram because it all looks correct. You want to just do the eccentricity?
Yes, please.
Okay. So yeah, it's the distance, as it says there, it's distance between foci. And remember, the foci are these points here, right? If this is my semi-minor axis, this is my semi-major axis, and the foci are somewhere around here, right? And so this distance here would be the numerator, because as you said, it's the distance between foci and then the length of the semi-major axis. I'm sorry, the major axis, which is the whole thing, right? Semi-major is this half here, and then the major, of course, is the whole thing. So yeah, there's actually not much here, and I wouldn't expect much more than this on the test, because this is actually a very complicated thing that you need calculus to really fully understand. And it's already kind of hard. You don't really look at ellipses anywhere else, maybe in geometry, but why I'm saying that is because once you have this equation here, like, they're going to give you the numbers usually to count the eccentricity, right? And on the problem they give it to you, of course, I'll use scientific notation. Hopefully you're familiar with that. So that if that's 21,500,000, then it'll be 21.5 times 10 to the 6th. And 114,250,000 miles is simply 114.25 times 10 to the 6th. My 10 to the 6th cancel. And if I do 21.5 divided by 114.25, I will get whatever you have there, 0.188. Double check. I'm sure we did it right, though. Yes. And that is the eccentricity, which this thing tells us how elongated my ellipse is. So that picture is not even truly correct. It would be more elongated, right? It'd be like that.
Okay.
You might also see a question where you say, find one of the other ones, find the length of the major axis, right?
Mhm.
Given the eccentricity and the distance of the foci, given, E is equal to 0.56 and distance between foci, whatever. If he's actually doing planets, then yeah, sure, 18, million. And if this is true, well, what's the equation that relates everything? Well, E is equal to, distance between foci divided by length of the major axis. But if I want to find that, then I simply have to solve for it in our usual way that hopefully you're very familiar with by now. And the equation I would get is the length of the major axis, right, is distance divided by E. Is all that okay and clear? I know I went fast, but
Mhm.
okay, good. Because you might see that where they don't do that. So what else did you want to talk about on this one? Because to me, I've covered everything, but maybe there's a reason that you chose this.
I think I'm actually good on it. I just wanted to go over it to make sure
Okay,
I was thinking about it correctly.
good, smart. So yeah, like I said, that's one other piece. I don't know, it could be helpful. When E is equal to 1, the eccentricity is 1, that's a circle. There's no elongation. Like there's the semi-major axis is the same as the semi-minor axis. So
Mhm.
okay. Oh yeah, this is since we're here, might as well make sure you're good on Kepler's second law. Really, all of Kepler's laws, but you can't put that much on the final. You know what I mean? Like, how long do you have to take this thing? An hour or 2 hours?
Um, 2 hours.
2 hours. Okay. Yeah, but still, he can't put all of them on there. I mean, he could, but he probably won't. But Kepler's second law is the one I would really remember if you're not able to get them all, right?
Mhm.
Are you good on that? Do you want me to cover it, or do you want to move on?
Can we go over it, please?
Yes, of course. So ellipse, again, I'll try to draw a little better one. That's not much better. Sun or star, whatever. That's fine. Again, at one of the foci. And this is my my minor axis. The foci goes through there. And what it's saying, what Kepler's second law says, equal areas in equal times, right? They say way more
Mhm.
fancy than that, but the key is equal areas in equal times, which means if I have a planet, that's my blue one, well, it goes here, and I don't care where it is, it doesn't matter as long as the time is the same. Well, it goes that distance in some time t. That's fine. Okay, good for us. But look at this area. If we connect the foci from the star to the point, that's the second point, and then the star to that, this is an area of a sector. If you remember geometry, I don't think you have to worry about that. There's an area 1, maybe.
Mhm.
Now, as long as I don't care where it is, it could be literally anywhere on this path of choosing another one. But let's just say, okay, how about from here and then here, as long as it's the same time. So I've done it backwards. It needs to go a lot further than that. If we want to use Kepler's law, it needs to go like over here, right?
Mhm.
Time, again, the same time as this. That's the key point here. It has to be the same time. We can do the same thing, draw our lines. I'll do a dash one to denote the second one. And then there's an area 2, and the point of Kepler's second law, as long as these times are the same, well then A1 is equal to A2. As long as the times are the same, equal times, then equal areas. And the consequence, the most important qualitative part of this is that, well, the only way this can be true is if the planet moves slower out here. So watch me do this whole thing. It moves slower out here and it must move more quickly over there. That's what that means. That's the only way that this equation in Kepler's second law can be true. So let's say the planet starts here, or let's do it easier for me. So it's out here and it's kind of fast, but it slows down. It's slowest at its perihelion, and then it speeds up, and it's fastest right there until it does it again, right?
Mhm.
And that's Kepler's second law.
Okay.
Anything confusing? I don't want to use too much math, but hopefully the equation isn't too bad, right? I'm just saying equal areas, and because it really, you did focus on qualitative, and I don't want to put too much math into it when you don't need it.
Yeah.
So think you're okay on that one?
Yeah.
Okay, cool. So we looked at that ellipse, and I didn't see anything else on these pictures that you did send, except that were, definitions. It was displacement, mass, weight,
Mm-hmm.
Yeah, scalar quantity versus vector quantity. You good on those, you think? Like if you were to write down a definition.
Kind of.
Did you say kind of?
Yeah, I'm not really sure.
Okay, so and there's nothing wrong with that. So scalar means, this is what I said before, it's a number, 3 or a million. I don't care what number it is. Yeah, but it has units. This is a distance. We know that. 3 meters. There's a number, and then there's units. Fine. That's easy and simple. Why are you telling me this? Because we have to understand that to understand what a vector is. Vector quantities. Oh, okay. 3 meters, but now it's up. Now it's down.
Oh, okay.
Yeah. And what's the difference? This is a direction. So think about that, going to your house or going to the store, right? And you're trying to tell somebody to get to your house, and you say, go 2 miles. That doesn't help, right? Because you have to say, go 2 miles in this direction. That's the only way they can do it. And that's a good example of like a vector, right? So force is a vector because it matters the direction that I pull. Acceleration is a vector. Think about free fall, right? It matters that the direction is straight down. It would be, everything you've learned would be completely different if acceleration, the direction didn't matter, and say acceleration was up, right? That would be weird, and that's why vectors are important. So mass, time are the most common examples of scalars because it's just a number and some units. Usually people get thrown off by the units, but the point is it's a magnitude, like 10 seconds or 10 apples, 5 cats. Direction doesn't matter. I don't care about direction in the number of apples that I have, right? Yeah, displacement is a vector. Mass, I think you're hopefully okay on that. Inertia, is that the idea of inertia? I'm just picking ones that people usually have trouble with.
Can we go over inertia and Newton's laws?
Yeah, definitely. So body's natural resistance to any change in the state of motion. Okay, that's fine, but those are kind of complicated words. What does that mean? That means the larger the mass, the harder it is to move something. Imagine you go up to some big guy and you want to push him over. So he's really big, and imagine how hard it is. And you push on him or push on a wall. This thing has a lot of mass. And that's what inertia is. It's resistance to motion. You're trying to exert a force on this thing, but it's not going anywhere because it has a lot of mass. Now imagine you push some guy, but then you push a child over. And so a child is small. There's not a lot of mass, right? That's why it's easy. Not that I have any experience in it, but that's the idea. And that we were talking about the hockey players. That was the example that I think that we were using. And there's this giant hockey player. He's probably not too fast or too good. Maybe he's good. Maybe he's just a defender that's slow. And the little guy hits him and he falls into a heap or something on the floor. And because of Newton's third law, which says equal and opposite reactions. Little guy he's coming in hot, and he hits this big guy who's just standing there with a large force, right? Let's call it F. But Newton's law says, oh no, that's not it. That's not the end of the story. This big guy, even though he's just standing there, he still exerts the same exact force back onto him in the opposite direction. Now the key here is that this has a big mass. I can use big M for that, and this guy has a little mass. So we already applied that, Newton's third law. That's the equal and opposite forces, yes? But now Newton's second law says, okay, well, F net, or the total force, F net, or just big F, I'm going to use that because that's what I'm using in my problem, is equal to MA. And it is net. That is an important part. And this right here, this equation tells us why the little guy goes flying in a heap and this guy didn't even notice. Because of that. And that's what we call inertia. This idea that I said, the mass is not necessarily called the inertia, but everything that I'm trying to talk about is inertia. And remember, acceleration, like, it's a different equation, and it's a different context and different idea, but we just spent a lot of time on free fall, and weight equals mg. G is the gravitational acceleration, but it's still acceleration and always is. And so if this goes up, so imagine you have the same force like we do here. If this number is the same, if mass is large, then acceleration has to be smaller. And that's why the guy stands here. He's got a big mass. Plug that into there. If you have some of the same force, the acceleration is not going to be that high because of that equal sign. And this guy goes flying. Why? Because he has a small mass. So he's going to have a larger acceleration if we want to keep that number the same.
Okay.
Yeah, that's honestly everything pretty much with at least Newton's second laws and third, and action, reaction, force pairs, inertia. Force is fairly easy, hopefully. And then Newton's first law is just a special case of the second, that if there's no acceleration, well, it's not going to move. Or if there's no force, if there's no force, it's not going to move, right? That's what this change with uniform motion and remain at rest or moving. If you want to move something, well, you better have a force or change the motion, right? You got to have a force acting.
Okay.
All right. So that's what we got here. I wish you the best of luck. I honestly think you're going to do well. So please don't stress about it. It honestly just makes it worse. I know it's probably impossible not to stress. I don't know how you feel about tests in general, but hopefully,
Yeah.
confident. Do you get nervous?
Yeah,
usually?
I think so. Yeah, sometimes.
Yeah. Well, try not to listen. I'm confident. I think you're going to do great. So good luck.
Thank you. Thank you.
All right. Have a good night, Julia.
You too.